Hello everyone, welcome back to my YouTube channel. Let's assume you're given this kind of problem that says place a 3.0 kilogram block at the top of 3.4 meter high frictionless incline. At the bottom of the incline, the block encounters a spring with a constant of 400 Newton per meter on a gravitational surface. No energy is lost to friction. How far is the spring compressed? So how can we solve this problem? To solve this problem, we can use the principle of conservation of mechanical energy. But before that, let's look at the diagram for this problem. We are given, they say we should place a 3.0 kilogram block at the bottom of top 3.4 high. Therefore, we're going to have something like this. And we should place the block here, which is 3.0 kilogram. And the height from here is simply going to be 3.4 meters. And this experiences a force, gravitational force, right? No, sorry. At the bottom of the incline, the block encountered a spring with a constant force of 400 Newton per meter. This is going to be 400 Newton per meter. And we are asked to calculate how far the spring is compressed. So, first thing we need to do is to calculate the gravitational potential energy, which is known as GPE. Gravitational potential energy of the block that is on top of this. We need to calculate the gravitational potential energy. And gravitational potential energy is equals to mgh, where the m is given to be the mass of the block, g is acceleration due to gravity, and h is the height inclined. That is 3.4 meters. In this case, the mass of the block is 3.0 kilogram. Gravitational due to acceleration is 9.8 in meter per second. We are given the height to be 9.4 in meters. The only thing we need to do at this point is to multiply everything here. Our gravitational potential energy is going to be 3 multiplied by 9.8 multiplied by 3.4 meters, and this is simply going to be 99.96 joules. The next thing we need to do at this point is to find out how much kinetic energy how much kinetic energy of the block has at the bottom of this incline, which is there. Since the incline is frictionless, according to the statement we are given, if the incline is frictionless, all the gravitational potential energy at the top will definitely be converted into kinetic energy at the bottom. So therefore, if that is the case, we are simply going to have the gravitational energy, the gravitational potential energy will be the same thing as kinetic energy, or the kinetic energy will be the same thing as gravitational potential energy. If that is the case, we are simply going to have 99.96 joules, since that is something. Let me take a quick revision here. At this point, after multiplying everything, we have 99.96 joules. Next thing we need to do is to find out how much kinetic energy the block has at the bottom of the incline. Since the incline is frictionless, all the gravitational potential energy at the top will be converted to kinetic energy at the bottom. If that is the case, then the kinetic energy at the bottom will be equal to the gravitational potential energy at the top. That is how we get to find this. So, next thing we need to do is to consider that since at the bottom of the incline block is compressed, and this potential energy is stored as elastic energy, right? Therefore, invite the gravitational potential energy. Next thing is what? Elastic potential energy. We need to find that, which is in the spring. If that is the case, the formula for elastic potential energy is simply going to be a half kx squared. Sorry. At this point, the K simply stands for the constant, spring constant, which is 400 Newton per meter. And here we are given X, compression of the spring. That is what we need to find, this X. Meaning that we're focusing on elastic potential energy. The formula is a half kx squared. The K is, the spring constant, which is given to be 400 Newton per meter. And we need to find the X. Since all the kinetic energy at the bottom is converted into potential energy in the spring, therefore, we are going to have the 99.96 joules. 99.96 is simply going to be a half. Now we know the value of K, which is 400 Newton per meter. We are going to multiply that with x squared, and x squared is the unknown value. So at this point, we are going to solve for x, since x is unknown, and that is what we are asked to find. Making x to be the subject of the formula, x squared, sorry. Here we are going to have x squared is simply going to be, we're going to multiply everything by 2. We're going to multiply the 99.96 by 2 and divide that by 400 Newton per meter. Therefore, we're going to have 99.96. Remember the unit, which is joules. We're going to multiply that by 2, then divide everything by 400 Newton per meter. So, let me get my calculator. So if you multiply everything here and divide, you're simply going to end, we're going to put our answer in square root. If you multiply 99.96 by 2 and divide it by 400 Newton, here we're going to have the x squared is going to be what? 0.499 x in what? Meter square. For us to get rid out of the square root, we're going to square both sides. We are given x squared to be 0.499 meter square. So for us to get rid out of the square root on x squared, we are going to have x simply going to be the square root of 0.499. At this point, the unit meter square. If you punch on your calculator, the value of x is simply going to be 0.707 in meter. This will get rid out of this. So if that's the case, we can finally conclude and say the spring is compressed with approximately 0.707 meter. And this is it for this problem. I hope you found it very helpful. Feel free to like, share, and subscribe. Thank you.